The Atacama Desert in northern Chile, a unique stretch of empty land. No animals, no plants, no protection against the merciless sunlight, the driest place on Earth. Who would expect that this harsh landscape could be the home of one of the most advanced research installations that humankind has ever constructed? An astronomical observatory with the world's most powerful telescope. The home of a giant telescope to study deep space better than any time before, to probe the vast expanse of the cosmos right to the border of the observable universe. The home of the ESO Very Large Telescope, Europe's prime exploration base for astronomy. Cerro Paranal, the 2,630-meter-high mountain in the Atacama Desert, may be one of the most inhospitable places on our planet, yet it offers ideal conditions for an astronomical observatory. With clear skies, a stable and dry atmosphere, and no artificial light to disturb the sensitive measurements. The conditions found here made this mountain the primary choice of site for ESO, the European Organization for Astronomical Research. Night after night, specialist teams of scientists and telescope operators carry out observations of distant celestial bodies, some more than 10,000 million light years away. And the data they collect help tackle some of the most profound questions that humankind has ever asked. How old is the universe? How was it formed? How will it evolve? Is there life elsewhere in the universe? This is fundamental research at the cutting edge, and at the same time, it marks the highlight of a remarkable European success story. Since the days of Galileo, astronomy and technology have walked hand in hand. The combination of technology and scientific minds literally opened dramatically new vistas of the world in which we live and led to fundamental revisions of our world picture. Thus, by the beginning of the 20th century, astronomers had acquired a reasonably good, basic understanding of the solar system and the Milky Way galaxy. Yet many questions remained unanswered. What, for example, was the nature of the so-called nebulae, those misty patches in the sky? During the first half of the century, new telescopes, bigger and better than ever before, were built in the United States of America. They soon led to two major discoveries. The nebulae were independent stellar systems, remote galaxies with hundreds of billions of stars, and these galaxies were moving away from each other. The universe was expanding. With these discoveries, cosmology was born, an exciting new branch of astronomy, yet one that requires instruments that are large, complex, and expensive.
Very much of cosmology stems from the theory of relativity of Einstein. It has so thoroughly changed the concept that people had about time and space and the relation between time and space, that cosmology meant working out the ideas that Einstein had introduced.
At the same time, improving their understanding of our own stellar system was a priority for European scientists. This would, however, imply a new observatory in the southern hemisphere for Europe's astronomers.
How can we find out better the structure of the Milky Way, the constitution of our own stellar system, its population, its motions? And one reason is that the center of our own stellar system, the part of the system around which everything rotates, that center you can observe only from the southern hemisphere. And they were interested in the properties of the nearest of all the other stellar systems, and these are the Magellanic Clouds. That one can observe only from the southern sky.
In 1953, the German-American astronomer Walter Baade visited Leiden for a couple of months. In discussions with Jan Oort, the famous Dutch astronomer, the idea of a European observatory in the southern hemisphere was born. In June of that year, a conference was held in Groningen on the coordination of galactic research, to which most of the leading European astronomers came. During a boat excursion on the IJsselmeer, the matter was discussed thoroughly by the participants, and soon after, in Leiden, a declaration on the need for a European Southern Observatory was signed by prominent astronomers representing 6 European countries. A decade after the Second World War, European cooperation was emerging as the driving force for the development of the continent. In 1952, CERN, the European Organization for Particle Physics, then termed Nuclear Research, was formed. In 1957, the Treaty of Rome marked the birth of what was to become the European Union, setting the stage for a European integration of historical dimensions. And then, on the 5th of October 1962, at a ceremony in Paris, the ESO Convention was signed by representatives of Belgium, France, Germany, the Netherlands, and Sweden. An enormous challenge awaited the newborn organization: to establish an observatory, fully competitive with the best in the world, at a desolate desert site, thousands of kilometers away from Europe, and to help European astronomers regain leadership in their field of research. In 1963, the world of astronomy was thrilled by the discovery by the Dutch astronomer Martin Schmidt, who was working in the US, of an entirely new and enigmatic type of astronomical object to become known as quasars. They were found to be at enormous distances from us, giving a tremendous boost to cosmological research and underscoring that astronomy was a field of lively research. First to carry the ESO baton was Otto Heckmann, who, as Director General, set up his headquarters in Hamburg. Soon, a major question had to be addressed by Heckmann and the ESO Council: where to locate the new observatory. Even before ESO was formally established, a site testing team had been active in South Africa. However, new information, both from American astronomers and from a German astronomer, Jürgen Stock, indicated that Chile might offer superior sites. Indeed, selecting distant sites had become feasible. After all, by the early 60s, air travel had gone through a revolution, and intercontinental flights were becoming possible on a hitherto unknown scale. In 1964, the ESO Council chose a site on the southern outskirts of the Atacama Desert in Chile. A 2,460-meter high mountain, 600 kilometers north of the capital, Santiago. The saddle-shaped mountain became known under the name of La Silla, and construction began soon after. Meanwhile, in 1967, Denmark became the 6th member state of ESO, and in 1969, the new observatory was officially inaugurated by the Chilean President of State, Eduardo Frei Montalva. With the inauguration of the observatory, the responsibility for ESO passed to Adrian Blau of the Netherlands. His primary task was to find a solution to a serious problem that ESO had encountered. The main objective was to construct a 3.6-meter telescope at La Silla. However, building up an organization, developing the site at La Silla, and installing a series of telescopes took a heavy toll on the small ESO team.
My main effort after having become director of ESO, was looking for ways to realize that telescope project. And after exploring several avenues of collaboration, it turned out that the most promising would be seeking collaboration with CERN in Geneva. It turned out that CERN was very receptive to our proposal, that in fact they thought it would be a nice thing for their engineers to have to do with the challenge of building a big telescope. And from then on, it was decided through an agreement between ESO and CERN that they would help out, they would create space on their premises, they would make their engineers and other staff available, and from then on, in an amazingly short time, things developed so that I believe already within half a year after the contract was signed, our people were working in their own hall on the CERN premises. And that's what was then called the ESO TP division, the ESO Telescope Project Division.
In 1975, Lodewijk Volcher took over the helm at ESO.
So I came from Columbia University, where I had been chairman of the astronomy department for something of the order of 10 years. And I came really with the aim of making ESO fully competitive with the best what was there in the world. I wanted to have the opportunity to make ESO also a first-class scientific institution and not only a place where telescopes were built. Without it, of course, usurping the scientific privileges of the institutes in the member countries. And a small scientific group was established at ESO. We finished the 3.6, which of course was already well on its way to completion when I came. We started on modern instrumentation, because having a 3.6 meter telescope in itself wasn't doing any good if there weren't proper instruments.
On the 8th of November 1976, Sven Laustsen, project leader for the 3.6 meter telescope, could make his first entry in the observation log for the new telescope. The first astronomical target was 47 Tucani, the beautiful globular cluster in the southern Milky Way. With the 3.6 meter telescope completed, Europe's astronomers now had access to a telescope that could compete with other major facilities, and in addition under the southern skies, with their privileged view towards the center of the Milky Way and the Magellanic Clouds, the twin nearby satellite galaxies of our own stellar system. But ESO didn't stop here.
The 3.6 was there, and so it was time to think what one was going to do after the 3.6 would effectively function. It seemed that it was the moment to make a new beginning, to build a really substantial telescope that could do much more than the preceding ones. We proposed that in the Large Telescope meeting at ESO CERN in 1977, the end of 77, and then this very slowly became the project of ESO's future.
One of the early tasks of ESO was the systematic mapping of the hitherto relatively unknown southern skies. The tool for this was a Schmidt telescope, a giant photographic camera with a large field of view. The southern survey was a Herculean task, and ESO teamed up with an Anglo-Australian group to complete it. Night after night, year after year, the huge photographic plates registered the multitude of celestial objects in the southern sky. Many discoveries were made in the course of the survey. Thousands of galaxies were observed for the first time, but also objects close by, such as comets and asteroids, were captured by the powerful Schmidt camera. Photographic plates had been the key detector for astronomy for almost 100 years. However, towards the end of the 70s, a new type of electronic detector was introduced, the so-called charge-coupled device, or CCD. With the advent of CCDs, astronomical research went digital in an unprecedented way. A true revolution was in the making, and once more, astronomy as driver of new technologies was part of it. 20 years later, CCDs could be found in the simplest household cameras, and the digital revolution would form the base of an entirely new type of society, the information society. With the completion of the 3.6-meter telescope, ESO had gained in strength and confidence and was ready to stand on its own feet. By 1980, all ESO's activities in Europe came together at the new headquarters in Garching, near Munich, with the formal inauguration ceremony attended by Karl Carstens, President of the Federal Republic of Germany.
We do astronomy because it is beautiful and because it touches on the most fundamental issues of the nature of the universe we live in, the origin of the Earth and its evolution. To all who have come here to celebrate with us the completion of our new headquarters, welcome.
Around the same time, two countries, Italy and Switzerland, had begun negotiations to join ESO.
And that qualitatively changed the impact of ESO, not only scientifically, also politically, and it made possible 7 years later to get the VLT approved.
However, while ESO developed steadily, the world's astronomers had set their eyes on a very different observational tool, the Hubble Space Telescope, a project by NASA with the cooperation of ESA, the European Space Agency. In preparation of the deployment, in 1983, ESA chose ESO as the host institute for the Space Telescope European Coordinating Facility.
Quite apart from the benefits of tying the space telescope much more to ESO, it had also the advantage that it brought ESA and ESO much closer.
The new facility was to assist European scientists using this telescope, and the choice of ESO underscored the growing importance of ESO as the focal point for European astronomy. In 1986, Comet Halley was visible in the sky as it swung into the inner solar system. Returning every 76 years, this most famous of all comets has played an important role in the history of astronomy. Bearing witness to the capabilities of modern technology, the first detection of Halley's comet at La Sille took place almost 4 years earlier as a fuzzy point of light on a CCD image. And as the comet moved towards its perihelion, the closest distance from the Sun, a dedicated team of astronomers followed the comet for several months. One of the results was a spectacular series of observations by the Danish astronomer Holger Petersen, showing the rapid changes in the comet's dust and iron tails. Also, the following year saw an extraordinary, completely unexpected astronomical event. Known to astronomers as supernova 87A, a giant star suddenly exploded in the Large Magellanic Cloud, 170,000 light-years away. Supernovae provide the source of the heavy elements, and their study is exceedingly important. Most supernovae occur in very distant galaxies and thus appear very faint, but supernova 87A was the exception. It was close enough to be seen with the naked eye, in fact, the first visible supernova since 1604. The year 1987 was not just an exciting year as regards events in the sky. As the year drew close, ESO's council met at the Garching headquarters to consider the proposal presented by the Director General, Professor Volcher, for the construction of a giant astronomical telescope, modestly termed the ESO Very Large Telescope, or VLT. The meeting was also attended by the incoming Director General, Harry van der Laan. The proposal was contained in a 342-page document that, thanks to its cover, became known as the Blue Book. The Blue Book described a project for an array of huge telescopes with monolithic primary mirrors of 8.2 meters, far bigger than any other mirror ever produced. Clearly, the Council decision was crucial to ESO's future.
Then we had the vote by a show of hands, and it was unanimously approved. We knew we had a job, we had a challenge, we had a future, and I was aware when I would go back to Garching on the first working day of 1988 that we were facing the challenge of how to implement the Blue Book with the resources that Council had provisionally allocated on the 8th of December 1987. But of course the challenge was that the new program was per annum comparable in size to the entire ESO budget, per annum. And therefore this was a phase change for the organization.
The decision to build the VLT was a monumental decision. If successful, European astronomers would have access to a research facility second to none in the world. However, coping with this task would require deep changes at ESO, transforming it from an observatory not fundamentally different from other big observatories to a forceful technology and science organization with all the competencies needed to execute mega science projects. ESO also sought partnerships with leading national research institutes for the development of a suite of extremely powerful instruments, spectrographs and cameras that would be mounted on the VLT telescope. The strategy of involving national facilities not only ensured a unique and vital part of the VLT program, but also stimulated collaboration in research and development between the national institutes themselves.
Motion guides and moved by a spindle drive system.
It was clear that the very large telescopes of the future could not be realized with conventional technology. Innovative solutions had to be found. A milestone development was the invention of active optics by ESO optical scientist Raymond Wilson and his team. This revolutionary technology enables the use of thin telescope mirrors whose shape and relative position are precisely controlled by a computer-based support system. To test the concept, ESO built a new 3.5-meter telescope, funded by the entry contributions of Italy and Switzerland, and carrying the appropriate name, the New Technology Telescope, or for short, the NTT. In 1989, the NTT was ready to observe the sky, with spectacular success. Already in the first night, images were obtained that were dramatically sharper than with any other ground-based telescope.
And when the first results came in, we could hardly contain ourselves. I remember that at the time, some people said, this can't really be true. That the very initial experiments, the very initial observations, already more than met specifications.
Once again, the symbiosis between technology and scientific research were to open new perspectives for scientists. At the formal inauguration, a proud ESO Director General could declare,
I trust that the creative innovation, which the entity undoubtedly represents, will inspire ambitious collaborations because they make this house such a fascinating abode.
By the same time, another technology had seen the light of day, that of adaptive optics. Adaptive optics is an intricate system by which the disturbance of the starlight as it passes through the terrestrial atmosphere can be corrected. Fully developed, this technology enables ground-based telescopes to yield the same sharpness as if they were placed in orbit, like the Space Telescope. Working closely together with research institutes in France, ESO was strongly involved in this development. With a successful demonstration of both active and adaptive optics, the way lay open for the new generation of very large telescopes. Although the VLT was still a long way from completion, it had catapulted ESO into the league of major science organizations. In 1990, ESO presented itself next to CERN and ESA at a high-level conference in Rome, organized by the Italian Minister of Research, Antonio Ruberti.
From then it became clear that the European Union, or the European Community, as it was called at the time, became appreciative of the fact that some organizations, even older than the Treaty of Rome, were already fostering European links and setting up networks and performing on a continental scale, which was exactly what the European community aimed to achieve in many, many different sectors of society. And that in that sense, science had been a major trailblazer in establishing such modes of operation, in forging such links, and in weaving such networks.
By the end of 1990, ESO's council faced another major decision. Should the VLT be built at La Silla or at a completely new site, the Paranal Mountain, 600 kilometers further to the north, in the roughest part of the Atacama Desert? Already in 1983, ESO staff began monitoring the conditions at Paranal, and their data convincingly showed that Paranal was a superior site. Still, building on Paranal was a significant logistical challenge. Having weighed the arguments, the council vote in favor of Paranal was unanimous. Meanwhile, construction work for the VLT had begun at a number of factories all over Europe. Completely new manufacturing methods had to be developed, and for the primary mirrors, entirely new factories had to be erected for the purpose of casting and polishing them. The VLT construction involved scientists, engineers, and people of many different professions in industry, at national research institutes, and of course at ESO itself. All in all, more than 5,000 people were involved in the project.
It's only geometry, yes.
Others were already dreaming about it.
No.
Responding to a Europe-wide essay contest, young secondary school pupils described how they would like to spend an observation night with the VLT. 18 national winners were invited to visit ESO and observe with ESO telescopes. The essay contest gave birth to science careers for several of the young people. It also marked the beginning of a dedicated and sustained effort by ESO to involve the public and engage in educational matters, an effort that was to achieve considerable results a decade later. In 1993, US astronomers celebrated a giant new telescope known as the 10-meter Keck telescope, which, with impressive private funding, had been built in record time. The same year, the director of the Space Telescope Science Institute in Baltimore, USA, Riccardo Gicconi, took over the directorship of ESO. His task was to bring the VLT project to a successful completion, to transform the VLT from a project to a working machine.
When I arrived in 1993, I had some background in my career. putting together, starting the Hubble Space Telescope Science Institute, applying sophisticated data analysis technique to the handling of optical data, which had not really been the custom before. And the expectation that the building VLT, if done on reasonable time, and if it was done with high technology in all aspects, would be very good for astronomy in general, European astronomy in particular. And I think the sense of urgency that I tried to impart to the project had to do with the fact that clearly we were late with respect to the Keck telescope. And so we could expect for VLT to be successful if it carried out a very effective, efficient kind of observational program in which in a few years, in fact, VLT will have more data, gather more data than Keck did during its whole lifetime. And then to provide the means to actually utilize this data by providing very high quality instrumentation and very high quality data analysis. And that was pretty much the thoughts that I had.
Modern astronomy sees the universe as a giant physics laboratory. Here, nature offers the study of the emptiest of vacuums, the densest of materials, the lowest of temperatures, the highest of temperatures, and last but not least, incomprehensible scales of time and distance. But not everything happens far away, beyond the grasp of non-scientists. In 1994, the entire world was spellbound by the dramatic collision between Jupiter and comet Shoemaker-Levy 9. The comet, which had disintegrated before the collision, caused havoc in the atmosphere of the planet, releasing as much energy as millions of atomic bombs. At the safe distance of the Earth, the event caught the attention of the world media. For a week, ESO in Garching, one of the international information centers, saw intense media presence and a rather different encounter between the press and scientists, as the latter struggled to provide interpretations of their observations literally in real time.
It is, of course, very strange. This is immediately clear that something would only be observed so late during this impact. It could, of course, mean that, for whatever reason, there is a great delay between the impact and the actual visibility of this plume.
1 year later, another chapter in the history of astronomy was opened as Swiss astronomers Michel Mayor and Didier Queloz announced the first discovery of a planet in orbit around a star outside the solar system. The discovery sparked off intense competition between research teams in Europe and in the US, and the Swiss scientists installed a new telescope at La Silla, especially for the purpose of discovering extrasolar planets. For the VLT, under the leadership of project manager Massimo Tarenghi, both manufacturing in Europe and site construction in Chile were progressing according to schedule. In parallel, ESO began to develop an operational concept for the VLT based on the experience of the space telescope that would ensure the highest efficiency ever achieved for an observatory on the ground. In early November 1997, the first of the giant VLT primary mirrors ended its transatlantic journey on board MS Tarpon Santiago, with the safe arrival at the port of Antofagasta. Resting in a special container, the mirror was unloaded from the ship onto a specially equipped heavy load trailer. The convoy left the dock for the Paranal Observatory on the next day, accompanied by a substantial escort of local police, shipping agents, press and film crews, as well as many interested onlookers. Traveling with a speed of 3 kilometers per hour, 3 days later, it arrived safely on Paranal. The carefully planned method of transport, with all its precautionary measures, had proven to be safe and efficient. In March 1998, a paper by a group of mostly young astronomers electrified the scientific community. Carrying the title, Observational Evidence from Supernovae for an Accelerating Universe and a Cosmological Constant, the paper marked the conclusion of an extensive 5-year-long research effort and concluded that the expansion of the universe is accelerating due to a mysterious repulsive force that may dominate the universe. The finding, which was based on observations from the world's most important observatories, including La Silla, sparked lively discussions, much excitement, and incredulity by some. A steady stream of scientific results kept emerging from the observations at La Silla. In fact, with all its major optical telescopes and the only sub-millimeter telescope in the southern hemisphere in operation, La Silla was setting its mark on astronomical research as one of the scientifically most productive observatories in the world. Meanwhile, at Paranal, excitement was as widespread, but for a different reason. Soon, the first of the giant VLT unit telescopes would make its first astronomical observation. Astronomers call this first light, always an important event for an observatory. By May the 25th, the time had come. It's 10 p.m. Moments before first light, the atmosphere in the control room is tense. 20 years after the first ideas about a very large telescope emerged, 10 years after the project was approved, this is the moment of truth. The VLT incorporates the most advanced technology ever used in a telescope. ESO's engineers approached this ambitious project with great confidence, but now is the time to see whether they were right or wrong.
Yes. So it works. That's the one, huh?
Many thanks. 0.5. 0.5. Congratulations.
This is a great day for world astronomy. It marks the realization for the first time in this century of a ground-based optical and infrared astronomical capability which has been carried out by European effort and which is second to none in the world.
The first light images were stunning indeed. On the following day, they were presented at simultaneous press conferences in all the member states and the host country, Chile. These images made their way to front pages and TV news worldwide.
So the fact that it actually worked, that it worked at a level beyond, frankly, our expectations, was great. I mean, it was a wonderful, what I understood to be a wonderful step for science. And we really had control of the mirror surface, and therefore we could expect very, very high performance in as far as collecting area, that it was there, as far as angular resolution, as far as strain ratio, and all of those good things. And to me was, I must say, also quite surprising that so soon after first light we got to 0.27 arc-second, which at that time, in that wavelength range, was really exceptional.
First light was a major milestone, and soon, thanks to an ingenious design, the high manufacturing quality of its components, and a tremendously clever operations plan, the VLT would outperform every ground-based telescope on Earth. Yet, this was only the beginning. Indeed, the VLT has proved to be a formidable science machine, and European astronomers are now reaping a rich harvest of scientific results. These results include unique measurements of uranium isotopes in stars, observations that pave the way for a new and more accurate determination of the age of the universe. Other VLT observations address the question of the structure of the universe and its mass. From solar system research, studies of the Milky Way, to the most distant objects, the VLT is now making a strong impact on observational astronomy, with discoveries occurring at a breathtaking pace, as reflected by the steady stream of articles in scientific journals based on VLT observations. Many scientific results also find their ways into the public mass media, for the great new insights that astronomers gain are shared with the public. Astronomy is for everyone to enjoy. The scientific data are stored at the ESO Science Archive at the Garching headquarters and available online to scientists at their home institutes. The Science Archive itself, with its terabytes of data, plays a major role in an ambitious plan to create a virtual observatory, where scientists can obtain data from a number of sources for their individual research projects. The VLT is comprised of 4 major telescopes supplemented by auxiliary telescopes. The light from the telescopes can be combined so that the entire array functions as a giant interferometer. With interferometry, scientists can reconstruct images of celestial sources with a hitherto unseen sharpness. Hence, being able to master interferometry was a dream of observing astronomers. Indeed, optical interferometry is well understood in theory. However, conducting interferometry on this scale hadn't been done before, and certainly considered by many to raise almost insurmountable technical problems. But on the 17th of March 2001, the VLT interferometer carried out its first astronomical observation. ESO's Director General since 1999, Catherine Cesarski.
I was lucky to be the ESO Director General when the VLTI was tried for the first time. This was in March 2001. You know that the first thing that has been built about the VLT are these very large tunnels which contain delay lines, very complicated systems to allow you with an incredible precision to adjust the path lengths of the light that goes through 2 different telescopes looking at the same object. And if you do that right, then you can combine this light and you obtain what is called fringes, interferometric fringes. And we always thought that when we first tried the VLTI, we'll be working night after night after night to perhaps finally see fringes. In fact, on the very first night that the system was tried, immediately there were the fringes. They were really easy to find, and even better, once they were found, it was easy to keep them. The stability of the system turned out to be fantastic. The challenge is to do with the VLTI what we have already started doing with the VLT, to transform it into a system, to have the various subsystems work together and to put it at the service of the community. To achieve that, we are really pulling the forces, I would say, throughout Europe. Everybody is contributing know-how, intelligence, and high technology to achieve the VLTI. So from that point of view, I hope the VLTI will be a great success. We can say it will be a great European success. With this, we will have a system that will allow to obtain minute details of objects in the sky in an incredible way. We'll be able, for instance, to study Cephids, which are stars that pulsate. And from the study of these stars, we can get the best way of measuring distances in the universe. It is the way that has always been used, but the precision we will obtain with the VLTI is much better than anything that has been done before. We will also be able to look at young planets around young stars and measure their orbits, their masses, and this sort of thing. And finally, we will be able to look very, very close to the black holes that are in the center of galaxies, including our own.
Still, the emerging success of the VLTI is no reason for ESO to rest on its laurels. In its 40th anniversary year, ESO's council has given the green light for participation in the largest astronomy project at the beginning of the 21st century, the ALMA project. ALMA is the acronym for the Atacama Large Millimeter Array, a new project that also enhances ESO's expansion into non-optical wavelength domains. ALMA is an array of 64 12-meter radio telescopes to be placed at the plateau of Chajnantor at 5,000 meters elevation in the Chilean Andes range. The array will yield the same resolution in the millimeter and sub-millimeter wavelengths as the VLT in the optical band.
With ALMA, we will be able to look into objects that would appear completely dark to the VLT or the VLTI, such as stars that are really very, very early in their formation, very early planet formation in the same way, and also if we want to look very, very far away in the life of the universe, the very early galaxies will probably only be visible to ALMA. So we need ALMA from a scientific point of view, and with the construction of ALMA, we are also starting a new adventure. We are constructing on an equal basis a world-class facility with the North Americans, with some Chilean participation, and within Europe, we are again pulling the forces of all the sub-millimeter observatories on the continent.
ESO's participation in the ALMA project demonstrates its ability to stimulate cooperation. At the same time, ESO accepts the challenge of competition. While projects for future extremely large telescopes exist in the United States, ESO is developing ideas for a gigantic optical telescope called OWL.
Well, of course, astronomers have a lot of imagination, and we see very good reasons to want to go further. With the VLTI, when we are looking at the sky with two telescopes separated by about 100 meters, we can obtain the sharpness that we would obtain with a telescope of 100 meters. But obviously, we only collect light on two 8-meter telescopes. The next step would be to entirely fill this area, to have a 100-meter telescope.
OWL will be a radically different telescope than any existing facility, exploiting the most recent advances in technology and building on ESO's significant experience in developing and operating large telescopes.
This may appear like a very large step, but after all, when ESO went from the new technology telescope, 3.5 meters, directly to building 4 telescopes of 8 meters and the whole of the interferometer that goes with it, the technological challenge was enormous. And we are prepared to take yet again a technological challenge of the same level by going directly from the VLT to a 100-meter telescope. With a telescope of 100 meters, it would become possible to detect directly planets like our Earth close to stars over really quite large distances around us.
When completed during the second decade of the century, OWL will boost astronomical research as much as Galileo's first use of a telescope. ESO embarks on the new projects with professional confidence, reinforced by the recent accession of new member countries. With the signature by the Minister for Science and Technology, José Mariano Gago, Portugal joined ESO in 2001. Marked with a press conference at the historical Royal Greenwich Observatory, the United Kingdom became the 10th member state in 2002, the anniversary year. Science and Innovation Minister Lord Sainsbury.
I'm sure I speak for the entire UK astronomy community when I say how much we're looking forward to participating in ESO and taking advantage of its marvellous facilities. I also hope very much that the UK's participation will lead to a strengthening of ESO and a widening of its capabilities for astronomical research.
With several other countries expressing interest in joining the organisation, ESO is emerging as the natural focal point for European astronomy in the new century. While ESO develops ambitious plans for the future, life goes on at Paranal as the great ESO adventure continues. Today, the VLT and the VLTI are considered the most successful ground-based observational facilities, both in terms of technical capabilities and efficiency. Indeed, from a challenging high-tech project, they've evolved into an awesome science machine, turning out more scientific data than any other observing facility in the world. Transforming these data into knowledge and sharing them with the public is the task that Europe's scientists are facing. It's a challenge, but also a promise to carry on with humanity's epic quest to obtain a better understanding of the world in which we live.